The concept of wormholes has been a fascinating topic for both physicists and the public for decades. Popularized in science fiction, wormholes are often seen as the ultimate shortcut, a means of traveling vast distances across the universe in an instant. But are they just fictional devices, or do they have a basis in reality? Could they really exist? And if so, could they be used to travel through space and time? Wormholes are sometimes referred to as shortcuts through space and time, theoretical passages that connect two different points in spacetime. Imagine spacetime as a vast, stretched out piece of fabric. By bending the fabric in such a way that two distant points meet, we create a wormhole, a bridge through spacetime. This concept, first introduced in Einstein's theory of general relativity, could allow for faster-than-light travel and potentially even time travel. The idea of wormholes presents mind-bending possibilities for exploration, allowing us to ponder questions such as, could we travel to distant stars in the blink of an eye? Could we use them to explore other parts of the universe that were once considered unreachable? Or could wormholes provide a way to explore the past or future? As we dive deeper into this subject, we'll explore what wormholes are, their theoretical foundations, and how they might hold the key to faster-than-light travel and even time travel. By delving into the science of wormholes, we'll learn about their potential and the challenges we face in understanding and discovering them. The concept of wormholes arises from Albert Einstein's theory of general relativity. General relativity revolutionized our understanding of gravity, space, and time, providing the framework for understanding how objects interact with the fabric of spacetime. In Einstein's view, space and time are not independent of each other, but are part of a single entity called spacetime. According to general relativity, space and time are flexible, capable of being warped or bent by massive objects. Imagine a massive planet or star creating a dip in a stretched-out sheet. This dip is what we experience as gravity, pulling objects toward the source of the distortion. However, this concept of bending spacetime does not just apply to gravity. It also has profound implications for the possibility of wormholes. A wormhole is essentially a fold in spacetime, where two distant points in space are connected through a tunnel. This shortcut through spacetime could, in theory, allow for travel between distant parts of the universe in the blink of an eye, bypassing the long journey across the fabric of space. The theory of Einstein-Rosen bridges, first proposed by Albert Einstein and his colleague Nathan Rosen in 1935, suggests that such shortcuts in space-time are mathematically possible. According to this theory, the idea of a wormhole is essentially a bridge that connects two distinct regions of space-time. In this theory, the two ends of the wormhole are like mouths that are connected by a narrow, curved throat. If wormholes exist, they could be used to travel between distant points in space. Theoretically, they could even be used to travel to different times, creating a connection between the past, present, and future. Wormholes come in different types, and there are various ways they could function. One of the most exciting types of wormholes is the traversable wormhole. These are wormholes that could, in theory, be used for space travel. They would allow objects such as spacecraft or even humans to travel through them without being destroyed or crushed by the extreme forces inside. Traversable wormholes would need to remain open and stable, which is where the concept of exotic matter comes in. Exotic matter refers to a substance with negative energy density, which is different from any matter we experience in our everyday lives. Exotic matter would essentially work against the forces of gravity. Normally, matter has a positive energy density, meaning that it attracts other matter. However, exotic matter would have negative energy, meaning it would repel other matter. This repulsive force is crucial for keeping a wormhole open, as it would counteract the gravitational forces that would otherwise cause the wormhole to collapse. scientists speculate that exotic matter might exist in certain quantum states, like the Casimir effect, or in regions of intense gravitational fields, such as near black holes. However, exotic matter is still theoretical, and much more research is needed to understand if it exists and how it could be harnessed to stabilize wormhole. One of the most exciting and controversial aspects of wormholes is their potential connection to time travel. If wormholes connect two points in space-time, they could theoretically be used to travel back and forth through time. The idea of using a wormhole for time travel arises from the theory of closed time-like curves, which are solutions to Einstein's equations that allow for time travel. A closed time-like curve occurs when space-time loops back on itself, allowing an object to return to its own past. Imagine entering a wormhole at one point in time, traveling through space-time, and then exiting at an earlier point in time. In theory, this would allow for time travel. However, the idea of time travel raises many paradoxes, such as the famous grandfather paradox, where changing an event in the past could prevent your own existence. But despite these paradoxes, the idea of time travel through wormholes remains a fascinating area of study. If time travel were possible, it could revolutionize our understanding of causality and the nature of time itself. But the practicalities of time travel are far from being realized, and it remains a highly speculative area of theoretical physics. As we dive deeper into the nature of wormholes, we encounter the intersection of two of the most fundamental theories in physics, general relativity and quantum mechanics. While general relativity describes the behavior of large objects in spacetime, quantum mechanics deals with the behavior of particles on the smallest scales. These two theories are fundamentally different in their approaches and often conflict with each other. Wormholes as solutions to general relativity describe macroscopic phenomena. However, to understand whether wormholes could truly exist, we must consider their implications at the quantum level. In quantum mechanics, particles can exist in multiple states at once and interact in ways that defy classical physics. Some theories suggest that the quantum foam at the smallest scales of spacetime could give rise to microscopic wormholes. These tiny wormholes, if they exist, could help bridge the gap between general relativity and quantum mechanics. However, the existence of these tiny wormholes is still purely theoretical. The tension between general relativity and quantum mechanics is one of the biggest hurdles in modern physics. If we are to fully understand wormholes, we'll need a quantum theory of gravity that can reconcile these two theories. Even if we could theoretically create or find a stable wormhole, the amount of energy required to manipulate space-time and create a stable wormhole would likely be astronomical, far beyond our current technological capabilities. Scientists have speculated that we might need the energy of a star or even a black hole to create a stable wormhole, making the concept of traveling through one a distant dream for now. Wormholes have become a central theme in science fiction, where they are often used to facilitate faster-than-light travel. In movies like Interstellar and Contact, and TV shows like Stargate, wormholes allow characters to travel across vast distances or even through time. These fictional depictions of wormholes are grounded in real scientific theories, although they often take creative liberties. Stargate portrays a wormhole device that instantly connects distant planets, while Interstellar used a wormhole as a plot device to transport astronauts to another galaxy. These imaginative uses of wormholes fuel public interest and continue to spark curiosity about the possibilities they offer. While wormholes remain theoretical, they offer a glimpse into the mysteries of space-time and the possibility of exploring the universe in ways we've only dreamed of. They represent the cutting edge of theoretical physics, and despite many challenges that stand in the way, their allure remains strong. In the next segment, we'll dive deeper into the theoretical foundations of wormholes and explore the mathematical equations that suggest they could exist. To understand how wormholes might work, we need to dive deeper into the theoretical foundations that underlie them. At their core, wormholes are based on the ideas put forth by Albert Einstein's theory of general relativity. This groundbreaking theory revolutionized our understanding of gravity, space, and time. But how does relativity tie into the existence of wormholes? In Einstein's view, space and time are not separate entities. They form a single unified structure known as space-time. Space-time can be curved or warped by the presence of mass and energy, like how a heavy ball placed on a rubber sheet distorts its surface. When large objects, such as stars or black holes, warp space-time, they create gravitational fields that we perceive as gravity. For wormholes to exist, space-time itself would need to undergo extreme warping, creating a shortcut or tunnel between two separate points. The Einstein-Rosen bridge, a theoretical solution to Einstein's field equations, is often used as the theoretical foundation for wormholes. This bridge suggests that if space-time could be curved in a certain way, two distant points could be connected, allowing for faster-than-light travel between them. This bridge, first proposed by Einstein and his colleague Nathan Rosen in 1935, became the theoretical framework for wormholes. However, this solution of general relativity didn't take into account the extreme conditions that would arise within such a passage. It wasn't until later, in the 1980s, that the concept of traversable wormholes, wormholes that could, in theory, be used for travel, was fully explored by physicists like Kip Thorne. The key to wormholes is the exotic matter required to keep them stable. But what is exotic matter, and why is it essential for the functionality of a wormhole? To create a traversable wormhole, one must maintain a stable opening in space-time. Otherwise, the passage would collapse under its own weight. The concept of exotic matter comes into play here. Exotic matter would be a type of substance that has negative energy density, meaning it would have unusual properties compared to regular matter. Unlike regular matter, which attracts other matter through gravity, exotic matter would have a repulsive gravitational effect. This means it would push things apart instead of pulling them together. For a wormhole to remain open long enough to allow a spacecraft to travel through it, this exotic matter would be required to counteract the intense forces trying to collapse the wormhole. Without this negative energy, the forces involved in maintaining a stable wormhole would likely cause it to collapse before anything could pass through. The idea of exotic matter is still theoretical, and it has never been observed in nature. But its potential role in stabilizing wormholes makes it a crucial piece of the puzzle when it comes to the practicality of wormholes for space travel. In essence, wormholes require an exotic form of matter that we have yet to discover in substantial quantities. This exotic matter would hold open the wormhole's throat and prevent it from collapsing under gravitational pressure, making it a potentially viable passageway through space and time. But even with the theoretical framework for wormholes and the concept of exotic matter,
significant challenges remain in our ability to detect, create, or stabilize a wormhole. Let's explore the mathematical equations and physical theories that suggest wormholes could exist in the universe. The study of wormholes involves deep mathematics, particularly the equations that govern general relativity. Einstein's equations describe the relationship between mass, energy, and the curvature of space-time. To explain how wormholes fit into these equations, we need to understand space-time geometry, the structure of space-time, and how it behaves under the influence of mass and energy. The concept of wormholes is rooted in the mathematical solutions to Einstein's equations that allow space-time to be curved in such a way that two separate points are connected by a tunnel. The Einstein-Rosen bridge, a solution to Einstein's field equations, represents a wormhole connecting two points in space-time. This theoretical solution suggests that space-time itself can be curved and connected by a bridge that exists between two regions of the universe. But while the Einstein-Rosen bridge shows that wormholes are possible in the equations of general relativity, it doesn't provide a practical solution for creating a traversable wormhole. That's because, as previously mentioned, such a wormhole would collapse due to the intense gravitational forces without the presence of exotic matter. This is where the contributions of modern physicists come into play, who have expanded on the Einstein-Rosen bridge concept and developed more advanced theories on traversable wormholes. One of the most significant breakthroughs in the study of wormholes came in the 1980s, when Kip Thorne and his colleagues formulated the idea of a traversable wormhole. They showed that it might be possible to stabilize a wormhole using exotic matter, and that it could, in theory, allow for the passage of information or even physical objects between two distant regions of space-time. This theoretical framework for traversable wormholes involves complex equations that describe how space-time can be manipulated to create stable openings. These equations suggest that a wormhole could be created by manipulating the fabric of space-time, allowing for instantaneous travel between two points. But energy required to perform such a feat would be immense, likely beyond the capabilities of any technology we possess today. As we continue to explore the possibility of wormholes, it's important to consider the role that quantum mechanics plays in understanding the nature of space-time at the smallest scales. Quantum mechanics governs the behavior of particles at microscopic levels, while general relativity deals with large-scale phenomena like gravity and the curvature of space-time. The need for a unified theory of quantum gravity is crucial in understanding how wormholes could actually function in the real world. Physicists are still working on reconciling general relativity and quantum mechanics into a unified framework that could provide a deeper understanding of wormholes and their potential to connect distant regions of space-time. Until that happens, wormholes remain theoretical constructs, mathematical solutions to equations that describe a universe far more complex than we currently understand. Given the complexities and challenges involved, we must ask, could wormholes exist in the real universe? The mathematical framework suggests that they might, but how likely is it that they actually exist? And if they do exist, how could we detect them? Physicists are not entirely certain about the possibility of naturally occurring wormholes. While some theories suggest that wormholes could form in the extreme environments near black holes or the early universe, we have yet to observe any wormhole-like phenomena in the real world. However, there are a few tantalizing possibilities that might indicate the presence of wormholes. One possible scenario is that black holes, the enigmatic objects at the heart of many galaxies, could harbor wormholes within them. If black holes are indeed connected to wormholes, it could mean that we have yet to uncover the full nature of these cosmic giants. But the problem is that the conditions inside a black hole are so extreme that we would never be able to observe a wormhole firsthand. The event horizon.
Wormholes are often described as shortcuts through space and time, and the more we explore the concept, the more questions arise about how they could function in the real world. To understand whether wormholes could actually exist, we need to consider the challenges that come with creating and stabilizing them. The biggest question that arises when discussing wormholes is, how would we keep them open long enough for travel? At the core of this challenge is the need for exotic matter, a form of matter with negative energy density. Exotic matter would behave in the opposite way to the regular matter we are familiar with. Instead of attracting other objects through gravity, it would repel them. The concept of negative energy might sound strange, but it's rooted in established physics, particularly in quantum mechanics, which has shown that negative energy can exist under certain conditions. In order for a wormhole to be stable and traversable, the exotic matter would need to be able to counteract the gravitational forces that would otherwise cause the wormhole to collapse. Think of it like holding open the entrance to a tunnel. Without something to push against the walls of the tunnel, the pressure from the surrounding material would cause the tunnel to cave in. Similarly, without exotic matter, the gravitational forces of space-time would collapse a wormhole faster than anything could pass through it. While we have yet to observe exotic matter directly, there are theoretical examples of its existence. For instance, the Casimir effect, a phenomenon that occurs when two parallel metal plates are placed close to each other in a vacuum, creates a slight attractive force between the plates, which can be interpreted as a form of negative energy. This effect occurs in the quantum vacuum, a place where particles are constantly popping in and out of existence. Though the Casimir effect is incredibly small and not powerful enough to stabilize a wormhole, it shows that negative energy exists on a small scale. One possible source of exotic matter might come from the intense gravitational fields found near black holes. A black hole is a region in space where gravity is so strong that not even light can escape. At the center of a black hole lies a singularity where matter is compressed to an infinite point and space-time breaks down. Some physicists suggest that the extreme conditions near a black hole might be able to create exotic matter. However, the problem is that the environment inside a black hole is so hostile that we would never be able to send a spacecraft inside to observe this phenomenon firsthand. Another issue is the sheer amount of exotic matter that would be required to stabilize a wormhole. In theory, a small, stable wormhole could be held open with a few grams of exotic matter, but the amounts required for larger, more practical wormholes, capable of allowing humans or spacecraft to travel through them, would likely be enormous. This brings us to another challenge: the energy requirements.
In order to manipulate space-time in such a way that a wormhole can be created, an immense amount of energy would be needed. In fact, the energy required to create or stabilize a wormhole might be on the order of the energy output of an entire star or even greater. Right now, we do not have the technology to generate such vast amounts of energy. Physicists have theorized that one way to generate the required energy could involve black holes, particularly rotating black holes. These objects are some of the most extreme environments in the universe, and their properties could, in theory, allow for the creation of a stable wormhole. In fact, some solutions to Einstein's equations suggest that the rotational energy of a black hole could be harnessed to create a wormhole. However, this idea is highly speculative, and even if it were possible, it would require technology far beyond anything we have today. At the moment, the idea of creating or stabilizing a wormhole remains firmly within the realm of theory. We do not have the tools to directly observe wormholes, let alone manipulate them. But this does not mean that the idea is purely science fiction. It is grounded in solid mathematical principles, and physicists continued to study the properties of space-time to understand how wormholes could exist and how they might be detected or created in the future. Another major consideration in the study of wormholes is their potential for time travel. If wormholes could provide a shortcut through space-time, could they also be used to travel through time? The connection between wormholes and time travel arises from the idea of closed time-like curves, a theoretical loop in space-time that would allow an object to return to its own past. Some physicists have suggested that a wormhole could be used to create such a curve, essentially allowing for time travel. However, this idea raises a number of paradoxes that challenge our understanding of causality. The most famous of these paradoxes is the grandfather paradox. If you traveled back in time through a wormhole and changed something significant, such as preventing your grandfather from meeting your grandmother, you could theoretically erase your own existence. How then could you travel back in time if you had never been born? This creates a logical contradiction, and many physicists believe that time travel through wormholes would either be impossible or that the paradoxes would be resolved in ways we do not yet understand. Despite these paradoxes, wormholes remain an intriguing possibility for time travel. They have the potential to revolutionize our understanding of the universe and the nature of space and time. However, the scientific challenges of creating, stabilizing, and detecting wormholes are immense. At present, wormholes remain a fascinating idea that lies on the frontier of theoretical physics, with no clear path toward making them a reality. Despite these challenges, the study of wormholes continues to capture the imagination of physicists and the public alike. As our understanding of the universe grows, it's possible that new discoveries will bring us closer to understanding whether wormholes are more than just mathematical curiosities and whether they could one day provide the key to faster-than-light travel and time travel.
As we continue to explore the fascinating idea of wormholes, we encounter more intriguing possibilities and challenges. One of the most exciting aspects of wormholes is their potential to offer a shortcut through space, allowing us to travel vast distances across the universe almost instantaneously. But how might we actually detect a wormhole? And what would it take to create one? Could wormholes be found in the real universe? And if so, how would we spot them? At present, the idea of traveling through a wormhole is largely theoretical,
but some scientists speculate that they might exist in regions of space that are difficult to observe with our current technology. The most likely places where wormholes could exist are in the extreme environments around black holes and neutron stars, objects that already stretch our understanding of physics. These objects are incredibly dense and generate extreme gravitational fields, which makes them prime candidates for harboring wormholes. A key question is whether a wormhole could form in the environment of a black hole. Black holes are often associated with intense gravitational forces that warp space-time in dramatic ways. The idea of a wormhole forming at the center of a black hole, connecting two distant points in space, has been a topic of much speculation. However, the extreme conditions inside a black hole present significant challenges. The gravitational forces near the singularity at the core of a black hole are so intense that anything approaching it would be crushed. This means that if a wormhole were connected to a black hole, it would likely be non-traversable, meaning nothing could pass through it. The very nature of black holes, particularly their event horizon, makes it nearly impossible for us to observe or interact with any wormhole that might exist inside them. However, the possibility remains that black holes could serve as gateways to other regions of space, or even different times. Theoretically, if a wormhole were located at the event horizon of a black hole, it might be possible to enter the wormhole and emerge at another location in space-time. However, the immense gravity near the black hole would likely destroy anything that attempted to pass through. This paradox, the possibility that wormholes could exist inside black holes but could never be accessed, raises more questions than answers and is one of the biggest mysteries in modern physics. Even if wormholes do exist, another challenge would be detecting them. Since wormholes are, in theory, a warping of space-time, they wouldn't be visible like stars or planets. They wouldn't emit light or radiation in the way that we are used to observing celestial objects. Instead, detecting a wormhole would require us to observe the effects it has on the surrounding space-time. One possibility is that if a wormhole were to exist, it could cause gravitational lensing, a phenomenon where light from distant objects is bent as it passes near a massive object, creating distorted images. If we could detect such distortions in space, it might be an indication that a wormhole exists in that region. Some scientists have proposed that microlensing events, where light from distant stars is briefly distorted by an object in the foreground, could provide a clue to the presence of a wormhole. While these events are rare and difficult to detect, they might provide indirect evidence that wormholes exist. The idea of observing wormholes through the distortion of light is still speculative, but it represents one potential way that we could eventually discover these cosmic shortcuts. While black holes are often considered the most likely location for wormholes to exist, there are other regions of space that might harbor wormholes as well. For example, some researchers suggest that wormholes could form in the early universe, when space-time was much more chaotic and extreme. The conditions right after the Big Bang were so intense that the very fabric of space-time may have been warped in ways that created wormholes. These hypothetical wormholes could have connected different regions of the universe, allowing matter and energy to travel between them. However, the early universe is a time that we cannot directly observe, making it nearly impossible to detect any wormholes that may have existed in the past. One theory suggests that wormholes might be linked to the concept of the multiverse, the idea that our universe is just one of many parallel universes. According to some versions of this theory, wormholes could act as connections between different universes, allowing for travel between them. This idea of a multiverse raises even more questions about the nature of space-time and our place in the cosmos. If wormholes are gateways to other universes, then what does that mean for the fabric of reality itself? Could we be living in just one universe among an infinite number of possibilities? While wormholes offer exciting possibilities for interstellar travel and time travel, the reality of detecting and interacting with them remains a distant dream. The extreme conditions needed to create and stabilize a wormhole are far beyond our current capabilities. Additionally, the energy required to manipulate space-time and maintain a stable wormhole would likely be enormous. At present, the technology required to create a wormhole remains purely speculative. Nonetheless, the study of wormholes continues to be a crucial part of theoretical physics. Researchers are actively exploring new ways to understand the fundamental nature of space and time, with wormholes serving as a key area of focus. The more we learn about the structure of space-time and the potential for wormholes, the closer we come to answering some of the biggest questions in physics. Is it possible to travel faster than light? Can we access different parts of the universe, or even different times? And if wormholes are real, what impact would they have on our understanding of the cosmos? While the practicalities of creating a wormhole are still out of reach, the possibility that wormholes could exist in the real universe offers a glimpse into a future where space travel might be faster, more efficient, and more exciting than we ever imagined. The next generation of physicists, astronomers, and engineers may one day find ways to unlock the secrets of wormholes, paving the way for humanity's exploration of the universe and possibly even time itself.
As we continue our journey through the possibilities and challenges of wormholes, one of the most intriguing aspects remains their potential for interstellar travel. Imagine a future where humanity is able to traverse the vast distances of the cosmos, not through years of traveling at light speed, but almost instantaneously, thanks to the existence of stable and navigable wormholes. This dream of interstellar travel has been a central topic of both scientific discussion and science fiction for decades. But while wormholes may offer the possibility of crossing great distances in a fraction of the time, they come with their own set of complexities and unknowns that we must still explore. One of the key questions that remains is whether humanity will ever be able to take advantage of these theoretical shortcuts. Even though wormholes have been predicted by the equations of general relativity, no direct evidence of their existence has yet been found. The idea that such shortcuts might be scattered throughout the universe is tantalizing, but the true question is whether we could ever detect one, stabilize it, and travel through it safely. For a long time, wormholes have remained in the realm of theory and mathematics. But that doesn't mean they are out of the realm of possibility. In fact, researchers are constantly searching for new ways to test the principles that might one day allow us to access them. At the heart of wormhole travel is the concept of space-time itself. Space-time as we know it is the very fabric of the universe. It's a four-dimensional continuum that combines the three dimensions of space with time. The theory of general relativity tells us that this fabric can be curved by the presence of mass and energy. Large objects like stars and planets cause dips in space-time, which is what we experience as gravity. These curvatures in space-time are well understood, and this is how Einstein was able to predict the movement of planets, the bending of light, and the dynamics of large cosmic bodies. However, if space-time can be curved by mass, what would happen if we could fold it,
or connect two distant regions, creating a direct connection between them. That's essentially what a wormhole is, a shortcut through space-time. If you imagine space-time as a flat sheet of paper, then traveling from one point to another in space would be like drawing a straight line across that sheet. However, if you were to fold the paper, you would bring two distant points together, creating a direct connection. This is analogous to how wormholes could connect two distant points in the universe, bypassing the intervening space entirely. Despite the excitement surrounding wormholes, one of the biggest challenges remains the stability of these tunnels through space-time. A key factor in keeping a wormhole stable is the need for exotic matter that has negative energy density, essentially the opposite of the matter we encounter in everyday life. Exotic matter would have properties that allow it to counteract the forces that would normally cause a wormhole to collapse. Without this exotic matter, the wormhole would likely close up before anything could pass through it. This exotic matter would act as a sort of scaffolding to hold the wormhole open, enabling safe passage from one point to another. As we've already discussed, exotic matter has never been observed in large quantities, and while there are a few potential ways it might exist, such as in the Casimir effect or in intense gravitational fields like those around black holes, its actual properties and behavior remain theoretical. The biggest hurdle is that the amount of exotic matter required to stabilize a wormhole would likely be beyond our current technological capabilities. While we have learned how to manipulate small amounts of energy and matter, the kind of energy and exotic matter required to keep a wormhole open would be on a vastly greater scale. This makes the practical creation of wormholes a difficult proposition with today's science and technology. The issue of energy requirements also plays a central role in the feasibility of wormholes for human space travel. We have to consider not just the exotic matter required to stabilize the wormhole, but also the immense amount of energy needed to create or manipulate a wormhole. Some theorists suggest that the energy required to produce a wormhole would be on the scale of the entire energy output of a star or even more. The amount of energy needed to distort space-time on a large scale could easily exceed anything we are capable of producing with our current energy resources. This means that even if we could discover exotic matter and learn to manipulate space-time, we would need breakthroughs in energy generation and control on a massive scale to make wormhole travel a reality. In addition to the energy requirements, there is the issue of navigation. While the idea of traveling through a wormhole seems appealing because it would potentially allow us to bypass vast distances in space, the problem of controlling and navigating the wormhole remains unsolved. Wormholes, as we currently understand them, are highly unstable and could collapse in an instant. Even if we were able to stabilize one, there would be the challenge of ensuring that the wormhole remained open long enough for a spacecraft to pass through safely. And once through, we would need to ensure that the wormhole leads to the desired destination. In the case of time travel, things become even more complicated. While wormholes theoretically could allow us to travel through time, this introduces the possibility of paradoxes, such as the famous grandfather paradox. Could we travel back in time and change events that would prevent our own existence? These kinds of logical contradictions create challenges not only for the theory of time travel, but also for the physics that would govern such travel. Some physicists believe that closed time-like curves, the loops in space-time that might allow time travel, could be possible, But they also suggest that such paradoxes might be avoided by some form of self-consistency in the laws of physics, meaning that events in the past might be self-correcting in a way that prevents contradictions. The challenges of wormhole travel are not only limited to the physics of creating and stabilizing wormholes, but also to the potential effects they could have on space-time itself. Wormholes could create distortions in the surrounding space-time, which might have unintended consequences. For example, if a wormhole were created in a region of space, the surrounding gravitational fields might be altered, leading to unknown and possibly dangerous effects on nearby stars or planets. We also have to consider the potential effects of traveling through a wormhole. How would the extreme forces of space-time curvature and exotic matter impact human bodies or spacecraft? One of the more speculative ideas about wormholes is the possibility that they might provide a gateway to other universes. The idea of a multiverse, the existence of multiple universes, each with its own set of physical laws, has gained some attention in recent years. If wormholes could connect different regions of space-time, it's conceivable that they could also serve as portals between different universes. This concept opens up even more profound questions about the nature of reality and the universe we inhabit. Could wormholes lead to entirely different dimensions? What implications would this have for the nature of space, time, and existence itself? At the moment, we can only speculate about the true nature of wormholes and whether they could one day allow us to travel through time and space. Theoretical physics provides us with the equations and principles that suggest wormholes could exist, but the practical challenges are enormous. Our current technology, energy production methods, and understanding of exotic matter are far from being able to make wormhole travel a reality. But the search continues, and new discoveries in physics and cosmology may one day bring us closer to unlocking the mysteries of wormholes. Until then, wormholes remain one of the most exciting and mysterious ideas in modern science. As we delve further into the potential of wormholes, one of the most fascinating possibilities is their connection to the multiverse theory. The idea of multiple universes, each with its own set of physical laws, has intrigued physicists and cosmologists for years. If wormholes exist, they might not just connect different regions of our own universe, but could potentially link entire parallel universes, a concept that takes the idea of space travel to a whole new level. The multiverse theory suggests that our universe is just one of many, each with its own version of reality. These universes could vary in their fundamental properties, different constants of nature, distinct laws of physics, and even alternate versions of events and life. The idea of wormholes acting as bridges between these universes is an intriguing extension of the theoretical framework that connects them to our own universe. Imagine a situation where a wormhole doesn't just connect two far-off points in space, but opens a doorway to an entirely different universe. This could mean that traveling through a wormhole could lead you to an entirely new reality, with its own galaxies, stars, and even completely different laws of physics. If this is possible, the implications for our understanding of reality would be profound. It would mean that the universe we experience might not be the only one that exists. There could be countless others, each operating under different rules. The multiverse theory raises numerous questions. Could we travel from one universe to another? What would the physical effects of traveling between universes be? Would we even be able to recognize that we have entered a different universe, or would the transition be seamless? While the concept of the multiverse is still speculative, the possibility that wormholes could be the means to access these other universes is both exciting and thought-provoking. However, the concept of the multiverse and wormholes is not universally accepted among scientists. Some argue that the idea of a multiverse cannot be tested or observed, and therefore it lies outside the realm of scientific inquiry. The difficulty lies in the fact that if other universes exist, we have no way of interacting with or observing them directly. Without experimental evidence or observable data, some physicists consider the multiverse theory to be more of a philosophical idea rather than a scientifically grounded one. Despite the challenges, the concept of wormholes as gateways to parallel universes has become a popular topic in theoretical physics. If wormholes exist and can connect distant regions of space or even different universes, they could offer a way to explore realms that were once thought to be beyond our reach. While this is purely speculative at this point, it opens the door to a host of possibilities that could expand our understanding of the cosmos. Beyond the multiverse, wormholes could also have practical implications for space exploration in our own universe. While current space travel technology is limited to our solar system, the possibility of wormholes could change the way we explore the universe. Imagine being able to bypass the vast distances between stars and galaxies by traveling through a wormhole, cutting down what would normally take thousands or even millions of years into a journey that could be completed in mere moments. This brings us back to the idea of faster-than-light travel, one of the most exciting applications of wormholes. According to Einstein's theory of relativity, nothing can travel faster than the speed of light, which sets a fundamental limit on how fast we can travel through space. However, wormholes, if they exist, could allow us to bypass the speed of light limitation by creating shortcuts through space-time itself. Instead of traveling at the speed of light through the vast expanse of space, a spaceship could simply enter a wormhole and exit at a distant point in the universe, effectively circumventing the speed of light limitation. The idea of using wormholes for interstellar travel has captured the imagination of many, especially in the realm of science fiction. Films like Interstellar and Star Trek have portrayed wormholes as a means of instant travel across the galaxy, allowing characters to explore distant star systems without the need for prolonged journeys. While these depictions are often dramatized for storytelling purposes, they are grounded in real scientific theories, and physicists continue to study the possibility of using wormholes for practical space travel. In addition to the energy required to create and stabilize a wormhole, there is the issue of navigating through a wormhole once it's created. A spacecraft would need to enter the wormhole, travel through the tunnel, and exit safely at the other end. But how would we control the entry and exit points of the wormhole? Could we steer the wormhole, or would we be at the mercy of its natural curvature? Some scientists have speculated that it might be possible to manipulate the geometry of space-time to create a stable wormhole with controllable entry and exit points. This would involve using exotic matter and extremely advanced technology to stabilize and navigate the wormhole. However, as we've discussed, the practical challenges involved in creating such a stable and navigable wormhole are immense. For now, the concept remains theoretical, and much more research is needed to understand how such navigation might be possible. The potential for using wormholes as a means of space travel also raises the question of what happens to the laws of physics when we travel through one. If a wormhole could allow for faster-than-light travel, would that mean we could violate the principles of causality, the idea that causes precede their effects? Time travel, as a byproduct of wormholes, introduces the possibility of time paradoxes, like the grandfather paradox, where changes made in the past could alter the present. How could we avoid these paradoxes while still using wormholes for travel? In response to these paradoxes, some physicists suggest that the laws of physics might have built-in mechanisms to prevent such violations. For example, the Novikov self-consistency principle postulates that any event that could create a paradox would be impossible to carry out. In other words, the universe might correct itself to ensure that paradoxes don't occur, preserving the integrity of time and space. While this is an intriguing idea, It remains speculative, and it's unclear whether such self-correcting mechanisms exist. As we continue to investigate the possibilities of wormholes, we must also consider the philosophical implications. The idea that wormholes might enable time travel or intergalactic exploration challenges our conventional understanding of reality. It raises fundamental questions about our place in the universe, the nature of time, and the limits of human exploration. Could wormholes unlock the mysteries of distant galaxies, or could they offer us a glimpse into the past or future? What would it mean for humanity if we were able to travel to other universes or timelines? Despite the challenges and uncertainties surrounding wormholes, they remain one of the most exciting and thought-provoking concepts in modern physics. They represent the intersection of theoretical physics, cosmology, and imagination, offering a window into a future where space travel might not just be a dream, but a reality. The journey to understanding wormholes is far from over, and as our knowledge of the universe continues to grow, we may one day find that these cosmic shortcuts are more than just theoretical ideas. They could be the key to unlocking the secrets of the cosmos.
As we move forward in our exploration of wormholes, one of the most important aspects to address is the potential real-world applications of these theoretical constructs. While wormholes have often been discussed in theoretical physics and science fiction, the possibility of creating or discovering one remains a fascinating idea. But could wormholes really be more than just concepts? Could we actually use them to explore distant parts of the universe, or even achieve intergalactic travel? At the moment, we are far from being able to create or utilize wormholes for travel. The energy requirements, the need for exotic matter, and the extreme instability of wormholes make it unlikely that we could create one with our current level of technology. However, that doesn't mean the idea is completely out of reach. In fact, some scientists believe that advancements in both theoretical physics and technology could one day allow us to explore the possibility of wormholes more deeply. As we've discussed earlier, creating a stable and traversable wormhole requires exotic matter, matter that has negative energy and would counteract the gravitational forces that would collapse the wormhole. The problem is that exotic matter is still purely theoretical. While we've observed small-scale effects, such as the Casimir effect, which can produce tiny amounts of negative energy in certain conditions, we have yet to observe or manipulate significant quantities of exotic matter. Without this exotic matter, any attempt to create a wormhole would result in its immediate collapse. This is where the concept of quantum mechanics becomes especially relevant. Quantum mechanics, which governs the behavior of particles at the smallest scales, might offer new insights into the nature of space-time and how wormholes could function. Quantum fluctuations, which involve the temporary creation and annihilation of particles in empty space, may play a role in the formation of microscopic wormholes. These tiny wormholes could be formed naturally in the quantum vacuum, where space-time is constantly fluctuating. While these quantum wormholes are incredibly small and fleeting, they might provide a clue to understanding the larger, more stable wormholes that could one day allow for interstellar travel. For now, wormholes remain a theoretical possibility, and the technology required to manipulate space-time on the scale necessary to create or stabilize a wormhole is far beyond what we currently possess. The energy required to generate such a wormhole would be on the order of that produced by a star or a black hole, far more energy than any human-made technology could handle. Even if we could stabilize a wormhole, we would still face enormous challenges in navigating it.
One of the key challenges in traveling through a wormhole is the issue of time dilation. Time dilation is a phenomenon predicted by Einstein's theory of special relativity, where time appears to pass more slowly for an object in motion relative to a stationary observer. In the case of wormholes, traveling through one could potentially cause time to move differently for the traveler and those who remain outside the wormhole. This means that while a traveler could pass through a wormhole and reach a distant galaxy in a short period of time, centuries or even millennia might pass in the outside world. This time discrepancy could pose a significant problem for any long-term space missions, as the traveler would return to find that much more time had passed than they experienced within the wormhole. If this time dilation effect exists, it would not only affect the experience of the traveler, but could also present challenges in the context of communication. Sending information back and forth between a spacecraft traveling through a wormhole and people on Earth would become complicated by the time differences. As such, understanding the effects of time dilation is critical to understanding how practical wormholes could be for human space exploration. Another consideration when thinking about wormholes is the safety of traveling through them. The extreme forces that exist near a wormhole's opening could pose a significant danger to any spacecraft attempting to enter the wormhole. Gravitational forces near the event horizon of a black hole are incredibly strong, and if a wormhole were to form in a region with similarly extreme conditions, the forces could crush a spacecraft or destroy it before it had the chance to enter the wormhole. Some researchers believe that, in theory, wormholes could be created in low-energy environments or regions with weaker gravitational forces, potentially making them safer for human exploration. However, this remains speculative, as we have not yet identified any locations where stable, safe wormholes could exist. The discovery of a stable, traversable wormhole, if it were ever to happen, would be a monumental breakthrough in the field of physics. It would represent the first real evidence that space-time can be manipulated in ways that allow us to travel vast distances across the universe almost instantaneously. If we could harness this technology, the possibilities for space exploration would be limitless. We could travel to other star systems, explore distant galaxies, and even visit regions of space that are currently beyond our reach. In addition to interstellar travel, wormholes could also have profound implications for the future of time travel. If wormholes could connect different points in time as well as space, they might offer a means of traveling into the past or future. This could have significant philosophical and scientific implications. The ability to travel through time could change how we perceive the universe and our place in it. It could open up new ways of understanding history, causality, and the flow of time itself. However, the idea of time travel through wormholes raises many paradoxes and challenges. As we've mentioned earlier, the grandfather paradox is one of the most famous and difficult to resolve. This paradox suggests that if you were to travel back in time and change something significant, such as preventing your grandparents from meeting, it could prevent your own existence. How could you then go back in time if you had never been born? Some theories propose that the laws of physics would prevent such paradoxes from occurring by imposing restrictions on time travel. These theories suggest that if time travel were possible, the universe would correct itself to ensure that paradoxes do not arise. Despite these paradoxes, the idea of time travel through wormholes remains an exciting possibility for the future. However, we are still far from understanding whether time travel is physically possible or whether it would violate the fundamental laws of physics. Even without time travel, wormholes could still revolutionize the way we travel across the universe. The potential for instant travel to distant parts of the cosmos would allow humanity to explore other star systems, perhaps finding new planets, resources, or even extraterrestrial life. It could also allow for the exploration of some of the most distant corners of space, including the outer reaches of our galaxy and beyond. The search for wormholes and their possible use in space travel is an area of great interest and research in modern physics. As technology improves and our understanding of the fundamental laws of the universe deepens, we may one day find the answers to questions that have captivated humanity for centuries. The journey towards unlocking the mysteries of wormholes may take decades, centuries, or even longer, but the potential rewards for human exploration and discovery are immeasurable.
As we continue to explore the possibilities and challenges of wormholes, it's important to consider their potential impact on our understanding of the universe. Wormholes, as a theoretical concept, push the boundaries of what we know about space, time, and the laws of physics. Their existence would challenge many of the ideas we've taken for granted, fundamentally altering our view of the cosmos and our place within it. One of the most significant implications of wormholes is that they could potentially break the limits we currently understand about space travel and time. We've discussed how wormholes could offer the possibility of traveling vast distances across the universe almost instantaneously. But the more we think about it, the more questions arise. If wormholes do exist, what else could they tell us about the nature of space-time itself? The very concept of a wormhole requires us to rethink the way we perceive distance and time. In our everyday experience, space and time are two separate entities. We measure distances in miles or light years, and time in seconds, minutes, and hours. But the theory of general relativity, from which the idea of wormholes arises, tells us that space and time are not independent, but are part of a unified space-time fabric. A wormhole, then, represents a manipulation of this fabric, an alteration of space-time itself. Instead of traveling across a flat or curved space, we could travel through a shortcut, bypassing the normal progression of space-time altogether. The discovery of wormholes would force us to question our understanding of causality. The traditional view of cause and effect in time is that events unfold in a linear, sequential order. The past causes the present, and the present causes the future. If wormholes could allow for time travel or instantaneous travel across vast distances, how would this affect our understanding of causality? Could we, for example, travel back in time and alter events that have already happened? Could we create a new timeline by interfering with the past? The paradoxes associated with time travel, like the famous grandfather paradox, are one of the most complex challenges when it comes to wormholes and time travel. If you were able to travel back in time and change the course of history, such as preventing your own grandparents from meeting, could you still exist in the present? These kinds of logical contradictions challenge the very foundations of causality, and resolving them is one of the biggest hurdles in making time travel through wormholes a reality.
some physicists believe that the universe might have built-in mechanisms to prevent paradoxes from occurring. They suggest that self-consistency in the laws of physics would prevent any paradoxes, ensuring that time travel through wormholes might only occur in ways that do not violate causality. While time travel raises complex theoretical issues, the possibility of instantaneous space travel is perhaps more immediately fascinating. The idea that we could bypass the vast distances of space through wormholes opens up the possibility of reaching distant star systems or even galaxies in a fraction of the time it would normally take. This could revolutionize the way we explore the universe. Currently, even the closest stars to us, such as Alpha Centauri, are so far away that traveling to them would take thousands of years with our current spacecraft. But wormholes could make such long journeys feasible within a single human lifetime. The idea of using wormholes for interstellar travel has captured the imagination of many in the scientific community. The possibility of accessing distant stars, discovering new planets, and even encountering extraterrestrial life is one of the most compelling reasons why scientists are so interested in wormholes. If we could travel through a wormhole, we would open up an entirely new era of space exploration, one where the limits of distance and time no longer pose a barrier. But this brings us to another important consideration: the practicality of building or finding a wormhole. The energy requirements and technological limitations we've discussed so far make it unlikely that we could create a stable wormhole in the near future. Even if wormholes exist naturally, they might be difficult, if not impossible, to detect and interact with. As of now, the only wormholes we can study are theoretical ones, and no direct observational evidence has been found to suggest that they exist in nature. In recent years, however, advances in gravitational wave astronomy have provided us with new tools to explore the fabric of space-time. Gravitational waves are ripples in space-time caused by massive events such as the collision of black holes or neutron stars. These waves travel across the universe and can be detected by instruments like the LIGO detector. Some scientists believe that gravitational waves could provide us with a way to indirectly detect the presence of wormholes. If a wormhole exists, it might create distinctive signatures in the fabric of space-time that could be observed through gravitational waves. However, this remains speculative, and detecting such signals would require significant advancements in technology and a much deeper understanding of how wormholes might interact with space-time. Another possibility for discovering wormholes comes from the study of black holes. As we've seen, black holes are often associated with wormholes, particularly in the form of the Einstein-Rosen bridge. The idea that a wormhole could exist at the center of a black hole has been suggested by physicists for decades. However, the extreme conditions inside a black hole, particularly near the event horizon, make it unlikely that we would be able to detect a wormhole in this way. Theoretically, wormholes might exist in regions of space where black holes are found, but these environments are incredibly hostile to human exploration. While the idea of finding a wormhole inside a black hole is compelling, there are practical obstacles. Black holes are incredibly difficult to observe directly, and any attempt to approach one would almost certainly result in the destruction of any spacecraft due to the tidal forces and gravitational pull near the event horizon. Additionally, the extreme conditions near a black hole would make it impossible to study the potential wormhole inside without getting too close. One of the most exciting aspects of the search for wormholes is the idea that they could provide us with the key to understanding the fundamental nature of space-time. Wormholes are not just theoretical objects, they are potential windows into the very structure of the universe itself. If we could discover or create a wormhole, it would represent a breakthrough in our understanding of how space, time, and gravity work at the most fundamental level. In the end, wormholes represent one of the greatest challenges and opportunities in modern physics. They embody the intersection of theoretical physics, cosmology, and science fiction, providing us with a glimpse into the future of space exploration and our understanding of the universe. While we are still far from realizing the dream of using wormholes for practical space travel, their study continues to push the boundaries of our knowledge. As we learn more about space, time, and the nature of the universe, the possibility that wormholes could one day be a reality becomes more intriguing and perhaps more attainable than ever before.
As we move deeper into the theoretical world of wormholes, one of the biggest challenges we face is figuring out how to detect these mysterious structures in the first place. We've established that wormholes are theoretical solutions to Einstein's equations, but finding one in the universe would be a monumental task. If wormholes really do exist, how would we know? And even more importantly, if they exist, how might we study them and potentially use them for space travel? The problem lies in the fact that wormholes are not visible like stars or planets. They wouldn't emit light or radiation in the same way that traditional celestial objects do. This means that detecting a wormhole directly would be almost impossible using traditional methods of observation. However, scientists have proposed several innovative ways that we might be able to indirectly detect a wormhole by observing its effects on space-time or other nearby objects. One possible method of detecting wormholes is through gravitational lensing. Gravitational lensing occurs when light from a distant object, such as a star or galaxy, is bent as it passes through a strong gravitational field. This bending effect is similar to how a magnifying glass can bend light and make objects appear larger or distorted. In the case of a wormhole, the gravitational field it would create could warp light from distant stars, making them appear distorted or shifted. By observing the bending of light in a way that can't be explained by regular gravitational objects, we might be able to detect the presence of a wormhole. This method of indirect detection is promising, but it presents challenges. The bending of light caused by a wormhole would likely be very subtle and could be easily confused with the gravitational lensing effects caused by more conventional objects, like galaxies or clusters of stars. To detect a wormhole through gravitational lensing, we would need to observe a distinctive pattern in the way light is bent. This is not something we can currently detect with the instruments available to us, but future telescopes and advanced astronomical techniques may one day allow us to observe such patterns with greater precision. Another potential method of detecting wormholes is by studying the movement of matter and radiation around them.
If a wormhole exists and is stable enough to allow the passage of matter, we might be able to observe the behavior of nearby objects, such as stars or gas clouds, as they interact with the gravitational field of the wormhole. The gravitational effects of a wormhole could cause these objects to move in ways that don't fit the usual patterns of gravitational attraction from known stars or black holes. If we observed a star being pulled toward an invisible object or orbiting a point with no visible mass, it could be an indication that a wormhole is present. Similarly, if a wormhole allows for the passage of radiation, we might detect anomalies in the way light behaves as it passes near a wormhole. If light can pass through a wormhole, it could potentially skip over large regions of space and appear at distant locations, creating unusual patterns in the cosmic background radiation. Scientists could analyze these anomalies using data from instruments like the Planck satellite, which studies the cosmic microwave background to search for evidence of wormholes. While these methods of detection are promising, they remain speculative for now. As we've seen, wormholes, by their very nature, would be incredibly difficult to observe directly. The gravitational effects of a wormhole might be too subtle to detect with current instruments, and the amount of exotic matter needed to stabilize a wormhole may be too small to be observed easily. Even if a wormhole were discovered, the practicalities of studying it would be immense. How would we send a spacecraft through a wormhole, or even observe what's inside? We don't yet have the technology to make such an observation, and it's unclear what we would even find if we did. Despite these challenges, the search for wormholes continues to be an important area of research in theoretical physics and astronomy. As we continue to develop more advanced tools and technologies, we may one day discover ways to directly detect or even create wormholes. For example, advancements in gravitational wave astronomy could allow us to measure the warping of space-time in ways that were previously impossible. Gravitational wave detectors like LIGO have already opened up a new way of observing the universe, and future detectors might allow us to study the effects of wormholes on the fabric of space-time. Moreover, the study of quantum mechanics may offer new insights into the creation and stabilization of wormholes. Quantum mechanics deals with the behavior of particles at the smallest scales, and some theories suggest that wormholes could form naturally at the quantum level. These microscopic wormholes might be fleeting, but understanding them could help us unlock the secrets of larger, traversable wormholes. If we can manipulate space-time at the quantum level, we might be able to develop the techniques needed to create stable wormholes on a macroscopic scale. In addition to the scientific challenges of detecting wormholes, there are also the philosophical implications to consider. If wormholes are proven to exist, they would fundamentally change our understanding of space, time, and causality. The idea that we could travel instantaneously to distant parts of the universe or even move backward and forward in time is both exciting and troubling. It raises questions about the nature of reality, the laws of physics, and the future of human exploration. Wormholes challenge our traditional understanding of time and space. They force us to rethink concepts that we take for granted, such as the idea of linear time and the speed of light as an unbreakable limit. If wormholes exist and can be used for travel, what other limitations of space-time might we be able to overcome? Could we one day manipulate the very structure of space-time itself, creating not just wormholes, but new ways to control the universe? In many ways, the study of wormholes is a journey into the unknown, a journey that could lead to new insights not just about space and time, but about the fundamental laws that govern the universe. Whether or not we ever unlock the secrets of wormholes, the search for answers is pushing the boundaries of what we know and encouraging us to ask deeper questions about our place in the cosmos.
As we continue to explore the theoretical and practical challenges of wormholes, one aspect that remains incredibly intriguing is the idea of exotic matter. While we've touched on this concept briefly in earlier segments, it's essential to dive deeper into what exotic matter actually is, why it's necessary for wormholes, and what it could mean for future breakthroughs in physics. Exotic matter refers to a form of matter with negative energy density. It behaves oppositely to the matter we encounter in our daily lives, which typically has positive energy density. In the context of a wormhole, exotic matter would be required to keep the tunnel open by counteracting the immense gravitational forces that would otherwise cause it to collapse. To visualize this, consider that if we didn't have exotic matter to hold a wormhole open, the forces of gravity would pull the tunnel closed almost instantly, preventing anything from traveling through. So how does exotic matter work in the context of a wormhole? Space-time, as described by general relativity, is curved by the presence of mass and energy. Regular matter, like stars, planets, and black holes, causes space-time to bend in a way that creates gravitational pull. Exotic matter, on the other hand, would have a repulsive effect on space-time, causing it to bend in the opposite direction and preventing the wormhole from collapsing under its own gravity. The notion of negative energy is central to the idea of exotic matter, and while it sounds bizarre, it is not entirely without basis. Negative energy has been studied in quantum field theory, which describes the behavior of particles at microscopic scales. One phenomenon that has been observed in quantum mechanics is the Casimir effect, which occurs when two metal plates are placed in a vacuum. These plates experience an attractive force due to fluctuations in the quantum vacuum. While the force is weak, it can be interpreted as an example of negative energy at work. The Casimir effect offers a glimpse into the strange world of quantum physics, where the rules of classical physics no longer apply. But while the Casimir effect provides a theoretical basis for negative energy, it does not come close to providing the quantities of exotic matter that would be required to stabilize a wormhole. For a traversable wormhole to remain open, it would need an enormous amount of exotic matter to counteract the forces of gravity. This is one of the biggest obstacles in making wormholes a practical reality. To generate the amount of exotic matter needed, scientists speculate that advanced technologies might be required, technologies far beyond our current capabilities. Some have suggested that black holes, particularly rotating black holes, could be harnessed to generate the necessary conditions for exotic matter. In theory, the energy produced by a black hole could be used to manipulate space-time in ways that could create and stabilize a wormhole. However, these ideas are highly speculative and remain within the realm of theoretical physics. Despite the challenges, the study of exotic matter and its potential role in wormhole formation continues to be an area of intense interest. If we could somehow discover or generate exotic matter in large quantities, it could open up entirely new possibilities for space exploration. It could provide a practical solution to the problem of stabilizing wormholes and making them usable for interstellar travel. The potential for this kind of technology is vast, but it remains far from our reach at the moment. In addition to the issue of exotic matter,
there's another fundamental problem when it comes to wormholes: stability. Even if we could create a stable opening to a wormhole, how would we keep it open long enough for anything to pass through? As we've discussed before, the gravitational forces involved in creating and stabilizing a wormhole are immense. Without exotic matter, the wormhole would collapse almost instantly. But even with exotic matter, maintaining the stability of a wormhole over time is still a major challenge. One proposal for stabilizing a wormhole involves using a concept known as negative mass. In theory, if a wormhole were to contain negative mass, it would create a repulsive gravitational effect, helping to counteract the forces that would otherwise cause the wormhole to collapse. However, negative mass is another theoretical concept that has never been observed in nature, and it remains an open question whether it could be used to stabilize a wormhole. Just as with exotic matter, the challenge lies in finding a practical way to generate or manipulate negative mass on the necessary scale. Another issue with wormhole stability is the fact that they could be potentially affected by quantum fluctuations. The principles of quantum mechanics suggest that space-time is not a smooth, continuous fabric, but is instead subject to tiny, unpredictable fluctuations at the smallest scales. These quantum fluctuations could cause the wormhole to fluctuate in size or shape, potentially making it unstable. Some theories propose that quantum gravity, a theory that combines general relativity with quantum mechanics, could provide a more complete understanding of how wormholes might behave at the quantum level. However, quantum gravity is still an area of active research, and we don't yet have a full understanding of how it might affect wormhole stability. The search for stable, traversable wormholes also raises a number of philosophical questions. If we were able to create a stable wormhole, how would we use it? Would it be something that could be used for space exploration, or would it be restricted to only certain individuals or organizations? Could a wormhole be used to create a shortcut between distant parts of the universe, or would it only lead to specific locations in space-time? These questions are not just theoretical. They touch on deeper issues about access, power, and control over space exploration. Additionally, we must consider the ethical implications of wormhole travel. If wormholes could allow us to travel to other star systems, could they also lead us to encounter extraterrestrial civilizations? What would our responsibilities be if we discovered intelligent life in another part of the galaxy? Would we have the right to explore and colonize new worlds? Or would we need to establish ethical guidelines to ensure we don't cause harm to other civilizations? These are complex questions that go beyond science and physics and into the realm of ethics and morality. As we think about the potential for wormholes, it's clear that we are just beginning to scratch the surface of what might be possible. Whether or not wormholes exist remains a question for future generations of scientists to answer. But the study of wormholes has already provided us with profound insights into the nature of space-time, the limits of our current understanding of physics, and the possibilities for the future of space exploration. While the journey to discovering or creating wormholes may be long and difficult, the potential rewards are immense. The future of humanity's exploration of the cosmos may very well depend on the discoveries we make in the coming decades.
As we continue to explore the theoretical world of wormholes, it's essential to look at how future technologies might play a crucial role in making wormholes not just a theoretical possibility, but a reality.
Despite the challenges that come with creating or detecting wormholes, scientists and engineers are constantly innovating, looking for new ways to manipulate space-time and improving our understanding of the universe. Could the advancements of tomorrow allow us to one day utilize wormholes for space travel? One of the key areas of progress is in quantum computing. Quantum computers operate on principles of quantum mechanics, where particles can exist in multiple states at once, making them capable of solving incredibly complex problems. While current computers are limited by their ability to process information in a binary manner, quantum computers use quantum bits, or qubits, which allow them to perform calculations at exponentially faster rates. This type of computing could be incredibly useful in simulating and understanding the complex nature of space-time and wormholes. Quantum computing may eventually help us model the behavior of space-time in ways that were previously impossible. For example, quantum simulations could allow scientists to simulate the behavior of exotic matter and study how it might be used to stabilize a wormhole. It could also help us understand how quantum fluctuations affect space-time and how they might contribute to the stability or instability of a wormhole. If quantum computers can accurately simulate these scenarios, we might be able to better predict the conditions under which a wormhole could be created or stabilized. In addition to quantum computing, advances in materials science might play a role in wormhole creation. As we've discussed, exotic matter is essential for stabilizing a wormhole, but we don't yet know how to create it. Materials scientists are working on developing new materials with unusual properties that could potentially behave like exotic matter. For instance, materials with negative refractive index or negative mass might one day be discovered and used to manipulate space-time. The ability to control and manipulate these materials on a large scale could open up new possibilities for creating and stabilizing wormholes. Another important area of research is in gravitational wave astronomy. In recent years, the detection of gravitational waves, ripples in space-time caused by massive events like the collision of black holes, has opened up a new way of observing the universe. These waves are incredibly subtle, and until recently, they were nearly impossible to detect. But with the development of advanced instruments like the LIGO and Virgo detectors, scientists have been able to capture these waves, providing a new perspective on space-time itself. In the future, more advanced gravitational wave detectors might be able to detect distortions in space-time caused by wormholes. Since wormholes are essentially ripples in the fabric of space-time, they might create gravitational waves that are distinguishable from those created by black holes or other massive objects. If we could detect these specific gravitational wave signatures, we might be able to identify the presence of a wormhole and study its properties in more detail. This could be a crucial step toward understanding how wormholes work and whether they can be used for travel. The future of wormhole exploration also depends heavily on space propulsion technologies. Currently, our spacecraft rely on chemical rockets, which are incredibly limited in terms of speed. Even the fastest spacecraft ever built, like the Parker Solar Probe, would take thousands of years to reach the nearest star system. To make wormhole travel a reality, we would need to develop much faster methods of propulsion, methods that could allow us to reach the entrances of wormholes and use them for interstellar travel. One of the potential breakthroughs in propulsion technology is nuclear fusion. Fusion power is the process that powers the sun, and if we can harness this energy on Earth, it could provide an incredibly efficient and powerful way to propel spacecraft. Fusion-powered spacecraft could potentially travel at a significant fraction of the speed of light, allowing us to explore distant star systems and reach wormholes in a reasonable time frame. While fusion power is still in the experimental stages, recent breakthroughs in plasma physics and magnetic confinement show that fusion might be closer to reality than ever before. If we could develop these advanced propulsion systems, we might one day be able to reach a wormhole and use it for interstellar travel. In fact, some researchers suggest that the best way to discover wormholes might be to send autonomous probes to distant regions of space, using advanced propulsion systems and gravitational wave detectors to search for any anomalies that might indicate the presence of a wormhole. These probes could be the first step in an eventual mission to travel through a wormhole and explore distant parts of the universe. Even though the technology required to create or utilize wormholes is not currently available, the research into these concepts continues to inspire new ideas and breakthroughs. The study of wormholes pushes the boundaries of our understanding of physics and encourages the development of new technologies that could change the way we explore the universe. As we continue to innovate and develop new tools for space exploration, we may one day find ourselves in a position where wormholes are not just a theoretical concept, but a real and tangible means of traveling across the stars. The quest for wormholes is more than just a search for a faster way to travel through space. It's a journey into the deepest mysteries of the universe. By studying wormholes, we are asking some of the most fundamental questions about the nature of space, time, and reality itself. If we can unlock the secrets of wormholes, we might not only revolutionize space travel, but also gain new insights into the fabric of the universe and our place within it. Until then, the study of wormholes continues to captivate scientists, inspiring the next generation of researchers to push the boundaries of what's possible.
As we continue to push the boundaries of science and technology, it's important to consider the ethical implications of wormhole travel. The potential for instantaneous travel across vast distances of space and time raises important questions about how humanity might use such technology and what responsibilities we would have in doing so. What would it mean for our society and for the universe if we were able to harness the power of wormholes for space exploration and possibly even time travel? One of the first ethical concerns would be about access. If wormholes could provide a shortcut to other star systems or even different parts of time, who would have control over these pathways? Would wormhole technology be available to everyone, or would it be limited to certain governments or corporations? If we are able to travel vast distances in an instant, could inequality be exacerbated, with only the wealthy or powerful gaining access to the benefits of wormhole travel? This brings us to the question of exploration versus exploitation. As humans, we have a history of exploring new frontiers, whether it's the oceans, other continents, or outer space. However, our explorations have often led to exploitation. If wormholes were to open new doors for exploration, could they also open the door to colonization or resource extraction in distant worlds? Could we go from a peaceful exploration of the cosmos to exploiting planets and resources in ways that harm the ecosystems of other worlds? If we were to discover intelligent extraterrestrial life in another part of the galaxy, how would we interact with them?
Should we simply explore and learn from them, or would we have the right to colonize or interfere with their societies? The prime directive of non-interference in science fiction, which suggests that humans should refrain from altering the natural development of other civilizations, raises important ethical questions. If wormholes made travel to other civilizations possible, should we just observe? Or should we engage, exchange knowledge, or even form alliances with these beings? Another key ethical question concerns the use of time travel. If wormholes allowed us to travel through time, we could potentially go back and change the course of history. But what effects would this have on the fabric of reality itself? If we could travel to the past and change major historical events, could we create paradoxes that have unforeseen consequences, not just for us, but for the entire future? Would we have the moral right to alter the past to fix mistakes, or would this be a form of tampering with something beyond our understanding? Could such power corrupt us? In many ways, the ethical dilemmas surrounding wormholes are similar to those we face with advanced technologies today. As we continue to develop new tools that can manipulate the world around us, from genetic engineering to artificial intelligence, we must carefully consider the consequences of these technologies. The same will be true for wormhole travel. As powerful as it might be, wormhole technology could bring about unintended consequences if not carefully managed. The environmental impact is another important consideration. If we could create wormholes and use them for space travel, how would this affect the fabric of space-time? Would the creation of multiple wormholes destabilize the surrounding space, creating ripple effects that could cause unforeseen consequences for the entire universe? The impact of altering space-time could go beyond just the physical and technological. It could also have cosmological effects. Could wormholes in some way contribute to the destruction of the very universe they aim to connect? We do not yet understand the full implications of manipulating space and time, and it's important to proceed with caution. Moreover, if we do unlock the secrets of wormhole technology, how would we deal with the long-term consequences of opening a door to the universe? Could we unintentionally expose the Earth or humanity to dangers from beyond our understanding? Or would we, as a species, be ready to responsibly manage such incredible power? These ethical questions are not just hypothetical. They are deeply tied to our present-day technological advancements. As we develop the ability to manipulate genetic material, artificial intelligence, and space exploration technologies, we must constantly ask ourselves, how do we ensure these technologies are used for the greater good, and how do we prevent their misuse? The same principles will apply when it comes to wormholes. While the possibility of using wormholes to travel to distant stars or even across time is an exciting one, we must also carefully consider how humanity will handle such powerful technology. Another significant challenge is the political implications of wormhole technology. Who would control access to wormholes? If wormholes allow us to travel between distant parts of the universe, would international or intergalactic agreements need to be made about their use? Would certain nations or corporations have the monopoly on wormhole travel, creating an imbalance of power and access to resources in space? The geopolitical dynamics of a wormhole-driven society could be as complex and fraught as any we face today. The prospect of time travel through wormholes could fundamentally alter the way we view history. If time travel is possible, would we see history as something that can be rewritten? How would this change our perception of free will and causality? Would our understanding of responsibility, consequences, and the value of actions shift if we believed that we could go back in time to change things for the better, or worse? We might also have to confront the question of life beyond Earth. If wormholes provide access to other galaxies, could we encounter intelligent life forms that challenge our very understanding of biology, psychology, and even ethics? What would it mean for us as a species if we discovered that we're not alone in the universe, and that the alien life we encounter is far more advanced than us? The discovery of alien life and potentially a new form of intelligence would force us to confront questions about our place in the universe and our role in the broader cosmic community. While all of these ethical questions are speculative for now, they are nonetheless crucial as we look toward the future of scientific exploration. Just as we have worked to develop ethical frameworks for dealing with genetic engineering, artificial intelligence, and space exploration technologies, we will need to develop new frameworks to govern the use of wormhole technology. Responsibility will be the key to ensuring that wormholes, if they are ever discovered or created, are used in ways that benefit humanity without causing harm to ourselves or the universe around us.
As we think about the future of wormhole technology, we begin to realize that the implications are not just theoretical, but profoundly transformative for our understanding of the universe and our place within it. The idea that wormholes might someday offer shortcuts through space and time invites us to imagine a new era of exploration, one where humanity could potentially travel to the farthest reaches of the cosmos, or even across different periods of time. However, this raises even more fundamental questions. What does it mean to be human in a universe where the limitations of time and space no longer hold the same significance? How would such a breakthrough affect our philosophical and existential beliefs? One of the most profound questions is the idea of time itself. If we could travel through wormholes, could we rewrite history or affect the future? The concept of time travel has always been a subject of fascination and debate. It touches on the very fabric of causality, the principle that every effect has a cause and that events unfold in a predictable linear order. If wormholes allow us to move through time, they would challenge this notion and introduce the possibility of multiple timelines and parallel universes. Would traveling back in time create multiple versions of the past? Could we inadvertently alter history by interacting with it? The famous grandfather paradox illustrates the kinds of dilemmas that could arise from time travel. If you travel back in time and prevent your grandfather from meeting your grandmother, could you erase your own existence? If such paradoxes are possible, they could have serious consequences for the integrity of reality itself. Some physicists speculate that the laws of nature might prevent paradoxes from occurring by enforcing some kind of self-consistency principle, suggesting that while time travel might be possible, it would always align with the timeline that prevents paradoxes. In other words, the universe might correct itself, ensuring that events unfold in ways that don't lead to logical contradictions.
Another philosophical question raised by wormholes involves the nature of human existence. If we could travel vast distances in space and time, it would fundamentally alter our perception of human lifespan and human potential. Imagine if humans could use wormholes to travel to distant star systems, encountering new worlds and civilizations. Would this be a form of immortality for humanity, allowing us to live through ages, exploring new frontiers, while time passes differently for us on Earth? Or would this ability to travel through time and space cause us to lose touch with the very essence of human connection, the shared experience of living through time as we do now? Furthermore, the possibility of time travel opens up questions about our identity. Who are we if our memories of the past can be altered, or if the future is no longer fixed? Would time travelers be able to change the course of their own lives, leading to a version of themselves that's vastly different from the person who originally existed in their timeline? If we had access to a wormhole that could take us to the past or future, would we even recognize ourselves? This leads to broader questions about free will. If we can change events in the past or future, do we have the ability to shape our own destiny? Or is everything predetermined by the nature of space-time itself? These philosophical questions about time and identity also connect to deeper existential concerns. Humans have always sought meaning in the context of their lives, trying to understand our purpose and the nature of reality. If wormholes allow us to alter the fabric of time and space, they could fundamentally change how we view our existence. Could the concept of destiny lose its significance if we could travel freely through time, adjusting events to suit our desires? Would we still find meaning in our lives if we knew that time itself was malleable and open to manipulation? Furthermore, as we venture out into the universe, we might encounter alien civilizations. The ethical, philosophical, and cultural implications of this possibility are profound. How would we treat extraterrestrial life forms? If we discover intelligent life on another planet, what rights would we have to interfere with their societies or ecosystems? Should we adopt the Prime Directive, as seen in Star Trek, which prohibits interference in the natural development of other civilizations? Or should we engage with these civilizations, offering knowledge and cooperation in the hope of creating a more unified galaxy? The discovery of extraterrestrial life would also force us to rethink our place in the cosmic hierarchy. We have long believed that Earth is unique in the universe, the only planet to support life. If we were to encounter other life forms, particularly intelligent ones, we would have to confront the fact that humanity may not be as unique or as central to the universe as we once believed. This realization could either humble us, making us more connected with the rest of the cosmos, or it could have profound psychological effects, challenging the very foundation of human exceptionalism. In all these considerations, wormholes represent far more than just a tool for space travel. They challenge our fundamental beliefs about time, identity, and our place in the universe. They offer the potential to alter the very structure of reality itself, but they also force us to confront deep existential questions that have plagued humanity for centuries. The study of wormholes is, at its core, a study of what it means to be human in a vast and mysterious cosmos.
As we delve further into the implications of wormholes, we begin to realize that their potential not only extends to space travel and time manipulation, but also to our very understanding of reality itself. The discovery or creation of a stable wormhole could challenge some of the most fundamental assumptions about the universe, and it could drastically alter how we view our relationship with the cosmos. The impact on our technology, philosophy, and even the future of humanity could be profound. One of the most exciting and transformative aspects of wormholes is their potential to open up new frontiers in space exploration. Right now, humanity is limited by the speed of light when it comes to space travel. Even with the fastest spacecraft ever built, it would take us thousands of years to reach the closest star systems. But the theoretical possibility of using wormholes as shortcuts through space could bypass these vast distances, allowing us to reach distant stars, galaxies, and potentially even alien civilizations in a matter of moments. The ability to travel across vast distances in such short amounts of time would have profound implications for humanity's future. If wormholes were accessible, interstellar travel could become as routine as taking a plane ride across the Earth. We might explore planets in other star systems, colonize distant worlds, or even discover entirely new habitats for human life. This possibility would expand the human frontier beyond the confines of Earth, transforming us from a planetary species to a galactic one. However, the reality of such expansion also presents challenges. If we are able to travel through wormholes to distant worlds, the question arises, how do we manage the impact of our exploration on those environments? Could we encounter ecosystems that are fragile and easily disrupted? If we discover intelligent life on another planet, would we have the moral right to colonize or interfere with their development? These questions are not just theoretical, they are deeply rooted in the ethics of exploration and the responsibility that comes with advancing technology. Moreover, the physical journey through a wormhole, even if it were theoretically possible, is not without its own risks. The conditions inside a wormhole would likely be extremely unstable. The fabric of space-time itself would be stretched and distorted, subject to intense gravitational forces. Any spacecraft traveling through a wormhole would need to be equipped to withstand these extreme conditions, or else it could be destroyed. Understanding the exact nature of wormholes, whether they can remain stable long enough for travel, how to navigate them safely, and how to protect life forms within them, are all questions that remain to be answered by future generations of scientists. The discovery of wormholes could also have a profound effect on our understanding of time. If wormholes can connect different points in time as well as space, they would allow us to traverse history, to go back in time and visit ancient civilizations, or even change the course of past events. The ability to manipulate time itself raises numerous philosophical and practical concerns. For one, if time travel were possible, how would we deal with the effects of paradoxes? Would changes to the past cause irreversible alterations to the present? Or would the universe adjust itself to maintain consistency? The grandfather paradox, in which a time traveler alters an event in the past that prevents their own existence, remains one of the most famous examples of the problems that time travel could present. On a more practical level, time travel could also allow us to explore the future. Imagine being able to jump ahead in time to see how humanity develops, what new technologies emerge, or how the universe evolves.
Could we visit future versions of Earth and witness the unfolding of history in real time? The ability to explore the future would not only transform our understanding of time, but would also allow us to observe the long-term effects of the choices we make today. It could give us the opportunity to learn from the future, potentially helping us to solve problems like climate change or global conflicts before they become insurmountable. However, the risks of time travel cannot be underestimated. If we have the ability to alter the past, even with good intentions, how can we be sure that we are not introducing unintended consequences that could harm the future? Would time travel create a butterfly effect, where small changes to the past have massive and unpredictable consequences on the future? The ethics of time travel would require careful consideration, with mechanisms in place to prevent individuals from using time travel for selfish or harmful purposes. The prospect of interacting with alien civilizations also raises unique philosophical questions. If wormholes allow us to reach distant star systems, we might encounter intelligent beings whose cultures, technologies, and values are completely different from our own. This presents both opportunities and challenges. On one hand, we could learn from these civilizations, share knowledge, and create peaceful alliances. On the other, how do we ensure that we don't disrupt their development, just as we worry about colonizing distant planets and altering their ecosystems? The possibility of cultural exchange with alien species opens up profound questions about the nature of communication, understanding, and the responsibility of dealing with other forms of intelligence. Furthermore, encountering extraterrestrial life could have profound implications for human identity. For centuries, humanity has wondered whether we are alone in the universe, and the discovery of intelligent alien life would force us to reconsider our place in the cosmos. Are we truly unique, or are we just one of many intelligent species scattered across the universe? The realization that we are not alone could lead to a shift in worldview, forcing us to reconsider humanity's role not just on Earth, but within the galaxy and the universe. How would this affect our cultural, religious, and existential beliefs? How would we respond to the knowledge that we are part of a larger cosmic community? This shift in perspective could also change how we view the future of humanity. If we discover that intelligent life exists elsewhere in the universe, we may begin to see our species not as a singular entity, but as one of many civilizations scattered across time and space. This could inspire greater unity and collaboration on Earth, as we recognize that our survival might depend on cooperation with other life forms. Alternatively, it could also lead to conflict if we view these extraterrestrial civilizations as threats or competitors for resources. As we approach the potential reality of wormhole discovery and use, the implications for humanity's future are profound. The ability to explore distant stars, travel through time, and potentially encounter alien life would change everything we know about ourselves and our place in the universe. Whether we are ready for such power is another question, but it's one that will require careful thought, cooperation, and ethical consideration.
As we approach the final segment of our exploration into wormholes, we must take a step back and consider the broader implications of what wormhole technology would mean for the future of humanity. While the technical, theoretical, and ethical challenges of wormholes are vast, the very possibility of using them would redefine how we understand the universe, time, and space. Wormholes represent one of the most ambitious and speculative ideas in modern physics. The concept challenges the very fabric of reality itself. If we could discover or create stable wormholes,
we would have the ability to manipulate space-time in ways that are currently unimaginable. The potential to explore distant stars, galaxies, and even other universes is nothing short of revolutionary. But perhaps the most profound aspect of wormhole technology is its ability to bridge the gap between what we know and what we have yet to discover. It would allow humanity to take its first steps into the deepest corners of the universe, where the boundaries of our understanding are stretched thin. For now, wormholes remain a theoretical concept, existing primarily in the equations of general relativity and quantum mechanics. There's no direct evidence that they exist, and the technology required to create or stabilize one is far beyond our current capabilities. Yet the potential impact of discovering a wormhole or developing the technology to create one is immeasurable. The implications for space exploration would be transformative. If wormholes allow for instantaneous travel across the universe, we could overcome the enormous distances that currently limit our exploration efforts. Space missions that would otherwise take thousands or even millions of years could be completed in a fraction of the time. This would fundamentally change the way we approach the exploration of distant star systems, planets, and even galaxies. Humanity could extend its reach across the cosmos, exploring worlds we can only dream of today. But perhaps the most profound aspect of wormhole technology is its ability to bridge the gap between what we know and what we have yet to discover. It would allow humanity to take its first steps into the deepest corners of the universe, where the boundaries of our understanding are stretched thin. For now, wormholes remain a theoretical concept, existing primarily in the equations of general relativity and quantum mechanics. There's no direct evidence that they exist, and the technology required to create or stabilize one is far beyond our current capabilities. Yet the potential impact of discovering a wormhole or developing the technology to create one is immeasurable. The implications for space exploration would be transformative. If wormholes allow for instantaneous travel across the universe, we could overcome the enormous distances that currently limit our exploration efforts. Space missions that would otherwise take thousands or even millions of years could be completed in a fraction of the time. This would fundamentally change the way we approach the exploration of distant star systems, planets, and even galaxies. Humanity could extend its reach across the cosmos, exploring worlds we can only dream of today. But perhaps the most profound aspect of wormhole technology is its ability to bridge the gap between what we know and what we have yet to discover. It would allow humanity to take its first steps into the deepest corners of the universe, where the boundaries of our understanding are stretched thin. For now, wormholes remain a theoretical concept, existing primarily in the equations of general relativity and quantum mechanics. There's no direct evidence that they exist, and the technology required to create or stabilize one is far beyond our current capabilities. Yet the potential impact of discovering a wormhole or developing the technology to create one is immeasurable. The implications for space exploration would be transformative. If wormholes allow for instantaneous travel across the universe, we could overcome the enormous distances that currently limit our exploration efforts. Space missions that would otherwise take thousands or even millions of years could be completed in a fraction of the time. This would fundamentally change the way we approach the exploration of distant star systems, planets, and even galaxies. Humanity could extend its reach across the cosmos, exploring worlds we can only dream of today. But perhaps the most profound aspect of wormhole technology is its ability to bridge the gap between what we know and what we have yet to discover. It would allow humanity to take its first steps into the deepest corners of the universe, where the boundaries of our understanding are stretched thin. For now, wormholes remain a theoretical concept, existing primarily in the equations of general relativity and quantum mechanics. There's no direct evidence that they exist, and the technology required to create or stabilize one is far beyond our current capabilities. Yet the potential impact of discovering a wormhole or developing the technology to create one is immeasurable. The implications for space exploration would be transformative. If wormholes allow for instantaneous travel across the universe, we could overcome the enormous distances that currently limit our exploration efforts. Space missions that would otherwise take thousands or even millions of years could be completed in a fraction of the time. This would fundamentally change the way we approach the exploration of distant star systems, planets, and even galaxies. Humanity could extend its reach across the cosmos, exploring worlds we can only dream of today. But perhaps the most profound aspect of wormhole technology is its ability to bridge the gap between what we know and what we have yet to discover. It would allow humanity to take its first steps into the deepest corners of the universe, where the boundaries of our understanding are stretched thin. For now, wormholes remain a theoretical concept, existing primarily in the equations of general relativity and quantum mechanics. There's no direct evidence that they exist, and the technology required to create or stabilize one is far beyond our current capabilities. Yet the potential impact of discovering a wormhole or developing the technology to create one is immeasurable. The implications for space exploration would be transformative. If wormholes allow for instantaneous travel across the universe, we could overcome the enormous distances that currently limit our exploration efforts. Space missions that would otherwise take thousands or even millions of years could be completed in a fraction of the time. This would fundamentally change the way we approach the exploration of distant star systems, planets, and even galaxies. Humanity could extend its reach across the cosmos, exploring worlds we can only dream of today. But perhaps the most profound aspect of wormhole technology is its ability to bridge the gap between what we know and what we have yet to discover. It would allow humanity to take its first steps into the deepest corners of the universe, where the boundaries of our understanding are stretched thin. For now, wormholes remain a theoretical concept, existing primarily in the equations of general relativity and quantum mechanics. There's no direct evidence that they exist, and the technology required to create or stabilize one is far beyond our current capabilities. Yet the potential impact of discovering a wormhole or developing the technology to create one is immeasurable. The implications for space exploration would be transformative. If wormholes allow for instantaneous travel across the universe, we could overcome the enormous distances that currently limit our exploration efforts. Space missions that would otherwise take thousands or even millions of years could be completed in a fraction of the time. This would fundamentally change the way we approach the exploration of distant star systems, planets, and even galaxies. Humanity could extend its reach across the cosmos, exploring worlds we can only dream of today. But perhaps the most profound aspect of wormhole technology is its ability to bridge the gap between what we know and what we have yet to discover.